while everyone's sitting down, I will say, I'm not going to talk about it here, but we published an article in Science Magazine. You know, the biggest climate change we have is the annual cycle. And we looked hard at the annual cycle and the performance of climate models. And none of the climate models that have a climate sensitivity of less than 3 were able to come close. Well, we could rule them all out as being candidates for the real world in terms of climate sensitivity. It doesn't mean that you can't construct a model with a climate sensitivity of less than 3 that might satisfy the constraints of the annual cycle. But at the current time, none of the CMIP3 models or the CMIP5 models with a climate sensitivity of less than 3 can simulate the annual cycle with sufficient integrity to be candidates for the real world. All right? With a whole lot of economists here, I had to talk a little bit about the real system. All right, so we're going to talk a little bit about especially this period here after 1970. So let's begin. So this is the record. There's the warmest years over there. And this is the record since 1970. After about 1970 is when global warming really kicked in the sense that the temperature perturbations are outside of the bounds of natural variability. And you can fit a straight line to this. It's actually a pretty good fit, as it turns out. There's some scatter about this, as there is about the overall, when you look at the overall record. And you can see the biggest departure is actually 1998, which was the big El Nino year. All right? And so what do deniers do? They take 1998 and they put a curve like this on it and say, oh, look, it's cooling. Of course, it's really warming. If you take that period after 1998 and fit a straight line to it, it actually indicates that it's warming. And by the way, I'm using the NOAA record here rather than the Hadley crew record, so it's got a somewhat better depiction of the polar region. And you can also look at this period and say, has it happened before? And my gosh, looks pretty similar. Anyway, Steve Schwartz gave me a nice introduction on this. A lot of our work in recent times has been trying to understand the energy flows through the climate system. And so this does relate to climate change and to some extent to climate sensitivity and radiative forcing. And under no climate change, the absorbed solar radiation, which is the net here between the reflected and the incoming, and the outgoing long-wave radiation have to be in balance in some sense. I won't say anything at the moment about timescales. And with climate change, we have increasing greenhouse gases, which reduces the outgoing long-wave radiation. And so there's a net imbalance at the top of the atmosphere, which is pretty well reflected at the surface because the atmosphere has very little heat capacity. And so this is the net imbalance in the global energy. So how do we measure the net imbalance in the climate system from a standpoint of energy? We now have direct measurements from space. This is from the Ceres instrument of the absorbed solar radiation, the outgoing long-wave radiation, and the net. We can also take an inventory of where all of the energy has gone. And so we've been trying to do that. And we can also use climate models with specified forcings. There is another way, but I won't mention it because it's not useful at the current time. So the commentary on this is that the first method is not accurate enough in an absolute sense, but it's supposed to be good for relative changes, the change from month to month, from year to year, over the, since 2000 we've got the record, so over the 13 or 14 years that we've got the record. So this is the only way we can really do the absolute values. I've said that it's best here, but we wrote a paper that was published in Science saying that when we do this kind of thing, there seems to be some energy missing. And there are problems over time because the observing system keeps changing. And number 3 depends on, well, how good is the climate model? And secondly, how good are the forcings? And so we've touched on that from a different from a different standpoint here with regard more to climate sensitivity. So if we have more energy coming into the climate system, where does this energy go? Well, it does warm the land in the atmosphere, which is really what we're talking about when we're dealing with climate sensitivity. We're talking about the surface, global mean surface temperature record. A lot of the energy goes into the ocean, which expands the ocean and raises sea level. A lot of it goes, well, some of it goes into melting land ice. Greenland is melting, glaciers are melting, which also raises sea level because more water goes into the ocean. It melts Arctic sea ice and so on, and the subsequent water has to warm up. It also goes into changing the water cycle. It can evaporate moisture, causing changes in rainstorms, changing the cloudiness, therefore changing the albedo of the planet. And so this can also then alter the net radiation coming into the system by altering the absorbed solar radiation. Over 90% of the energy, however, goes into the ocean. This has already been mentioned. So looking at one method now, looking at CCSM4, which it was commented before, is actually a pretty good model. And here we've run the model 8 times with perturbations to it. And what I'm showing here is the ensemble average from 1850 on. And this last part, this part here, is just blown up down the bottom. So if you want to see a blow up, you can just look down the bottom. It's identical. And here you can see these big dips in this record are all due to volcanic eruptions that have been put in at the time or close to the time when they were observed. And then this is one standard deviation about the ensemble average. And that value, in terms of monthly values, is actually 0.62 watts per square meter for the standard deviation. So that's a surprisingly large value from the model. And it turns out this is quite consistent with the series data also. And so there's quite a lot of fluctuations in this energy imbalance from one month to the next. And this is then caused mostly by changes in cloudiness. So we have a big storm, it generates a lot of cloud, it blocks the sun, but it's gone the next few weeks, and the system recovers, and a lot of that averages out. I've got here also the 12-month running mean. This is not reduced by the square root of 12, which is what you would expect if it's entirely random, because, as I will show you, we also have interannual variability associated with El Nino, decadal variability, and so on. So here's the values for the 12-month running mean. I'm actually showing the 8 ensemble members here, and in fact, as you can see, they all pretty well fit within the 1 standard deviation monthly values. And you can see the fluctuations in here. So this is natural variability that is occurring within this model from one run to the next. The El Niños occur at different times. They're not constrained. And then, as I say, this is the value for the 12-month running mean value. Looking at this overall, you'll see that the net energy imbalance is close to 0 up till around 1960 or thereabouts, and then the energy imbalance increases, and you've got these sharp volcanic eruptions that are included in here. These are just the major ones. There's a lot missing here. There's an overall increase in aerosols, which is included in this record as well, but it's highly idealized, and the way in which the volcanoes have been put in here are somewhat idealized as well. So in terms of the model forcings, it's somewhat idealized. Note the values as we come to the end. It's around an energy imbalance of 0.9 watts per square meter. All right? Now, here's the... pardon? The same model, identical model. In fact, the only perturbations were different months, different days of the week were used to initialize the atmospheric, and then it just developed in a chaotic fashion. So there were not even big perturbations that were put in. I've worked with Magdalena Barmacida at ECMWF, who probably have the best ocean data assimilation system that exists at the moment. It's not perfect, but nonetheless, it does assimilate all of the available data, all of the ocean data from Argo floats, the surface information from sea surface temperatures, the surface fluxes, the winds, and all of the sea level information, which after 1992, which is from altimeters from space. And this is the record of the ocean heat content from the ECMWF reanalysis in 10 to the 22 joules. This is the top 300 meters here. This is actually an ensemble system also, by the way. There are 5 members here which reflect uncertainties in things like the surface fluxes and various things. This is the top 700 meters, and the 0 here is for the first, I think, 5 years or something like that, 8 years back here. And then this is down to the bottom of the ocean. So here you do see this leveling off, in particular, after about 2003 in the top 300 meters, which is more reflective of what's happened at the surface in some ways. But when you go to the bottom of the ocean, you do not see this leveling off to anything like the same extent. But this is not a very simple curve. Back in here, the observing system is really poor prior to 1970, and I don't know whether you should pay any attention to this back in here at all, except I'm going to show you something here in just a minute. And there's quite a bit of character to this. And this is really for the first time. We haven't seen this in ocean temperature records that have been reconstructed before to anything like the extent that we're showing here. And what I want to highlight here is the fact that for the first time in an ocean heat content record, we're actually seeing signatures of the 3 major volcanic eruptions that have occurred in this period. And so there's a sharp cooling here with Agung and with El Chichon, with Pinatubo. And I've also identified something interesting in here in 1997-98. You can see that actually continues on. This is an arbitrary length of time I've got here for some time. And there was a huge cool down of the ocean, both the tropical Pacific and, in fact, the global ocean, following that particular El Nino event. 1998 was the warmest year in the 20th century. It was a time when the ocean was cooling. The energy imbalance at the top of the atmosphere was negative. So there's some rules, there's some things associated with this. We've actually got the warmest year on record at a time when the planet is actually cooling, because the heat is coming out of the ocean and contributing to the warmth at the surface. Now, it turns out this happens on decadal timescales as well, and it happens also always in association with El Nino events. So this has some lessons in some ways for interpreting what we're going to be talking about here. So here's the, I'm just looking now after 1980. This is down to 700 meters. This is the record we were just looking at. And the thing I really want to do is to convert this into rates of change. This is not an easy thing to do. And if you do this with most of the ocean heat content records that exist from other sources, you will find that they're all over the place with incredible amounts of noise. It's documented in a paper which we've got here. But these are 12-month running means. You can see now a bit more what's happening with regard to these perturbations that are indicating the uncertainty with these 5 ensemble members. So here's the actual rates of change that you can see is quite variable over this record through here. This is what it looks like for the total depth. Now I've put it behind here, and in fact through here you can't see much difference, and then after about 1998 you can see the purple a little bit higher than the blue, and in fact the difference, the average difference in the 2000s is 0.21 watts per square meter going to the full depth versus the top 700 meters. So 0.21 watts per square meter is going into the deeper part of the ocean. Now that's actually important, but it's really only after 1998. The other things on here, these are the time of the volcanoes. This volcano, if you look closely at this record, this drop actually occurs in March of 1982. What we're looking at is, with the 12-month running mean, is we actually look ahead so that it starts to drop, 5 months ahead of that particular date. So that's what you're actually seeing there. But these are actually very reasonable numbers, as it turns out. So I'll show you that right now. So what happens if we put these together? Now I've got in the background here the ensemble values and the 1 standard deviation from the model, along with these values for the entire record with 5 ensemble members of this ocean heat content put together. So firstly, let's look at the volcanoes. Here's Mount Agang. Given the state of the observing system at that time, this is pretty remarkable agreement, I think, between these two things. A lot of this must be coming from the sea surface temperature record, I suspect. Here's Pinatubo. Again, I think you would expect to see that it's slightly broader, so it doesn't quite have the magnitude, but I think this is actually excellent agreement from what you would expect. Now here, for El Chichon, there's a difference. And it turns out, using this, we were able to go back at the record, and we saw that the way they put El Chichon into the model, they had an idealized function attached to it, and it has a delay of about 6 months in terms of when the peak occurred in the model and when it occurred in nature. And it actually shows up here as a delay. There's some interesting things going on here, because it turns out, in association with all of these, there were El Nino events that caused complications. And in fact, you can see this goes way up very quickly. And what I've marked on here also are all of the El Nino events. And so if you look carefully on here with the El Nino events, at the end of the El Nino events, you see a cooling, in fact. Here's 97, 98. So here's this big cooling that's going on through here. And so El Nino events are causing a lot of the variability. Now, what about the overall agreement? I don't know. In here, these values in the ocean are a bit higher than we're expecting based on the model. Here, they're definitely lower. This is Pinatubo and the 97, 98 El Nino event. Given this is plus or minus 1 standard deviation, perhaps this is not too bad. Let's see. This is the actual values of the aerosol optical depth. So these are volcanoes and things which are not included in the model, small volcanoes and things like that. And notice there's a peak in here, and there's a sharp dip actually occurs in the ocean heat content. Wonder whether those two things are related or whether it's just a consequence of the El Nino event. There's some extra things that are worth exploring there. So anyway, my comment on this is that there's, not unreasonable agreement, but maybe the model doesn't have quite enough variability. Some of it might be because there's missing forcings. The forcings are not quite accurate. The fluctuations from year to year are not accurate. Maybe it's not too bad. Anyway. Now, looking at the more recent period, what I'm showing you now is the series record along with some error bars on it and an extra error bar with the dotted curve, which relates to the stability of the overall orbit to some extent. And here, the energy imbalance is sort of set to 0.8 watts per square meter, which is designed to fit with the ocean heat content. So the ocean heat content from RS4 is also plotted on here, and you can see in this earlier part here, it's a bit higher than the series values, and in the latter part, it's a bit lower. And then I've got some other values here, which are this is from Argo. This is, let's have a look down here. Karina von Schuckmann is estimate based upon Argo. So neither of these have anything in the Arctic, for instance, and also nothing in Indonesia or in marginal seas. And they are offering quite good support for the RS4. RS4 probably also doesn't have enough in the Arctic going on, I would say. That it's not a region that's been a major region of attention. There's other information. I could show you another figure which only goes down to 700 meters, where we've got a whole bunch of other ocean analyses that tend to support certainly these high values in this early part of the record here. So here I would say there's not great agreement between these two things. We published an article on this about missing energy. In 2010, and both of these records, the series record, the ocean heat content records, have been revised, and they've found about 20%. In other words, they've both come together a little bit. I think they still have to come together a little bit more, but this is sort of the state of the art in terms of the energy imbalance. So there's not great agreement between these. At times there are some marked discrepancies, and here's the I don't have time to do this. So anyway, this is the record for the last 1970 on, showing El Nino events and La Nina events, showing these drops that occur following the El Nino events. And here's the big one here. And because of the more consistent La Nina events in recent times, it relates to this Pacific Decadal Oscillation. And I don't have time to go into this, but the Pacific Decadal Oscillation has been defined based upon analysis of sea surface temperatures, departures from the global mean in this region here, and then projected onto the globe. It looks like this, and this is the time series associated with it. So the time series annual values looks like this. And so we can define then the positive and negative phases of the Pacific Decadal Oscillation. And this negative phase here is the phase which you have blamed on aerosols, but which I'm going to blame on the Pacific Decadal Oscillation. All right. And here we're in the negative phase here. And so if we simply take this period here after 1998 and compare it with this period through here and look at a few quantities, this is the difference now for this period, the so-called hiatus period, versus the previous period here, and it looks like this. These are total values. This is using actually the GIS, the NASA record. And so you can see massive warming over land and in most places, but cooling all throughout the central and eastern Pacific. So the place that has not warmed is this region here in the central and eastern Pacific, and over the southern oceans, by the way. This is the change, the same sort of thing, in terms of sea level pressure, which are the colors. These are high pressure systems, and then low pressure systems. Big low pressure system here extending up to here and down and through here. And so if you look at this, there's low pressure here. There's a wave train actually right down through here. And then these are the wind anomalies going on here. And this is 1 meter per second. And for such long periods, these are very large wind anomalies. And so there's especially strong trade winds in the Pacific that are piling up water over in the western part of the Pacific here, for this period, 1999 to 2012, extending well down into the subtropics. And then there's this wave train structure down in here. This is this low pressure system here. This is the region where the biggest increase in Antarctic sea ice has occurred. And it's associated with these winds. And there's been a huge loss in Antarctic sea ice in the Antarctic Peninsula. And so this actually accounts for part of that pattern. And then there's a spectacular pattern going up to the north. And I want to look at that from the North Pole perspective to see what that looks like. And I would suggest to you that there's actually a wave train across the pole. And the pole, of course, is where, so here's higher pressure, anticyclonic conditions, a lot less Arctic sea ice, maybe some feedback effects, but this thing has extended across into Europe, and this is the region where they've had some very cold winters in recent times in association with this pressure gradient here, which is the negative phase of the North Atlantic Oscillation. So this is mainly occurring in wintertime, and so there's some structure that we can actually relate in a wave train structure back to what's going on in the Pacific in association with this Pacific Decadal Oscillation. If we look at the ocean heat content, this is the top 100 meters. We see this pattern in a very striking fashion. Down to 700 meters, the contours have doubled here and doubled again here. This is down to the bottom of the ocean. And so there's extra heat going on in here, mainly in the top 300 to 400 meters of the ocean, where this pattern is occurring. So this has got a lot of resilience attached to it now, thermal capacity, if you like. And the main increase below 700 meters is in the Atlantic and over the southern oceans, as it turns out.
How dense is the network for the whole ocean?
For the whole ocean now, it's quite dense. There's about 3,200 Argo floats out there, but prior to 2004, there weren't. Pardon?
But these don't go
They go down to 2,000 meters. There's nothing much below 2,000 meters anyway.
So when you say the whole ocean, you're talking about 2,000?
Mainly 2,000 meters, yeah. I could do down to 2,000 meters. You wouldn't notice any difference. This is the changes in sea level over the period. You know, sea level altimetric measurements started in 1993. And if we blow up the Pacific here, this is what it looks like in the Pacific. Here, the rate of sea level rise is over 10 millimeters per year, over 8 inches over the 20 years that's been going on. And here's the Philippines here. So I can't resist putting high N in here, going right over this very high sea level, extremely warm water, so that even as the typhoon churns up the water, it gains more warm water from below in an exceptional fashion, which is also related to the specific decadal oscillation. So climate sensitivity, here's the formula. You've seen this before. I wanted to highlight especially the work from Otto et al., where they came up with a number of a central value of 2.0. But if you use our ORAS4 heat content values, this number here changes, and the climate sensitivity immediately jumps from 2 to 2.5. And if you use other numbers for these things, such as 3.75, I think that was also Steve's number. I don't know why they use 3.44, and different numbers for delta T, you can easily crank this number up to 2.9. So put a big cross over that, and it's very sensitive to which ocean heat content values they use. So that's mostly it. You know, this is the summary here of the fact that there's identifiable volcanic signals now that we can identify. The ocean has warmed at an unprecedented rate in the last decade or so, at the time when there's a hiatus in surface temperatures. There's a lesson there. And about 30% of that warming is below 700 meters. It's very much related to the changes in the winds, the specific decadal oscillation pattern. The Earth's energy imbalance varies from day to day with clouds and weather. It varies from year to year with ENSO. It has sharp drops with volcanic eruptions. It varies with the Pacific decadal oscillation. And during the positive phase of the PDO, more heat is deposited at shallow depths from 1976 to 1998, which is when the main warming that we've seen has been manifested, while in the negative PDO phase, more heat is deposited below 700 meters depth, and it's not then as apparent at the surface. It doesn't mean that the planet isn't warming. And so for the 2000s, you know, it went from order 1 watt per square meter to about 0.7, and the quiet sun played a role from 2003 to 2009 and minor volcanic activity, but there's certainly evidence that the planet is warming, and it's doing all these things. And so this is the thing related to climate sensitivity, but all of these other things can play greater or lesser roles as time goes on. So this is the thing that worries me more about climate sensitivity. You know, what about all of these other things and the kinds of things that I'm talking about here? Thanks.